Okay, thank you, Edith and Abhi, for the invitation, and thanks all for coming even on the start deadline. So today I'll be talking about quasi-linear size PCPs with small soundness from HDX. And this is joint work with Dor Minzer at MIT and Nikhil Vyas at Harvard, and Ziwei Yun, who's at MIT, graciously agreed to write an appendix to our paper, Constructing HDX. And this work builds on a recent line of works with Noam Lifshitz on direct product testing, and similar works results were shown by Yotam Dixty, Eric Dinur, and Alex Lobotsky. So let's start with what are PCPs. So let's start with a real world scenario where someone publishes a proof of P equals NP on the archive, which happens almost every day. So how do you check where it's wrong? So one thing you could do is go through it line by line and find the mistake. But the PCP theorem tells us that there is an efficient encoding of the proof such that you as a verifier can toss some random coins, check two locations in this proof, and verify that they satisfy some constraint, and either accept or reject. So formally, we have the guarantee that if you as a verifier would accept correct proofs with probability 1 and reject wrong proofs with probability at least 0.01. And of course, this is not specific to P equals NP, but holds for any NP language. So suppose you're given a 3-sat formula phi, and your task is to decide whether it's satisfiable or unsatisfiable. The PCP theorem tells us that you can encode a satisfying assignment in a format where as a verifier can toss a bunch of random coins, and if phi is satisfiable, then there exists a proof, green proof, on which the verifier accepts with probability 1. And if phi is unsatisfiable, then the verifier would always reject with probability at least 0.01. So let's actually take a more convenient view of the PCP theorem in terms of constraint satisfaction problems. So using this proof plus verifier system, let's build the following constraint satisfaction problem. So we have, for every location in this proof, we have one vertex. And for every 2 queries, we have an edge. And the constraint on every edge is the check that the verifier performs. And now using the PCP theorem, you get that if phi is satisfiable, then psi is satisfiable. And if phi is unsatisfiable, then every assignment to psi can only satisfy 0.99 fraction of the constraints. And this will be denoted by the value of psi. So in words, we have a polynomial time reduction from 3-sat to the language of deciding constraint satisfaction problems with completeness, soundness. And another parameter that we will care about today is the size, which is the blow up in this reduction and is the number of variables plus the number of edges inside. So any questions? Okay, so this theorem had a lot of remarkable consequences. Firstly, to hardness of approximation. So as might be evident, if you assume that deciding 3-sat is hard, then you immediately get that actually checking whether the value of constraint satisfaction problems is 1 or bounded away from 1 is also hard. And not just this, but it was shown using the PCP theorem that you get the optimality of many approximation algorithms for combinatorial optimization problems. And not just these, but you have many surprising applications to things like delegation of computation and cryptography. So this is remarkable, but we can always hope for better. So one question that arose after the PCP theorem was that how small can we make both of these parameters? And any improvement here would translate to some improvement in the downstream applications. So let's see what was known for these two-query PCPs with better size. So the work of Polishuk-Spielman showed that actually you can get pretty close to linear size while paying in the soundness. And then there was a long line of work, and some of the works I haven't mentioned here, culminating in the work of Dinur that showed a reduction, which incurs a mere polylog and blow up in the size, while getting the same soundness that is obtained in the PCP theorem. And for today's talk, we will only think about two-query PCPs and where the alphabet size is a constant. So then the question arose whether we can push this soundness close to 0. And because we are focusing on two-query PCPs.
What is two-query again?
Yeah, two-query is where we are looking at constraint satisfaction problems over two variables. Yeah.
So this number just looks at two locations and.
Okay, 2 bits.
Yeah, so because we only look at two queries, this is not immediate, whether we can push the soundness close to 0. And I will discuss what are the issues in building such PCPs with almost 0 soundness. So there was this question remaining whether we can get nearly linear size with soundness close to 0. And a few years later, Moshkowitz-Raz showed that you can do this, but with this 2 to the square root log n blow up. So one question that you can think is whether we can achieve the size that the Dinur's PCP gets while getting the soundness of Moshkowitz-Raz. Where here we think of epsilon as a constant. And this is what we answer. So we show a reduction from 3-SAT to 2 CSPs such that for all epsilon, there exists some constant such that in this reduction, if phi is satisfiable, then you get a satisfiable CSP psi. But if phi is unsatisfiable, then the value of the resulting CSP is at most epsilon. And the size blow up is going to be polylog n, where the constant in the polylog will depend on epsilon. So any questions?
Sorry, do you mean the exponent depends on epsilon?
Yeah.
Of the log?
Yeah, the exponent of the log depends on epsilon, and also the alphabet size of the CSP depends on epsilon.
Do you know to calculate this C or to bound it by function of epsilon?
So this constant is going to be exponential in polynomial in 1 over epsilon. This exponent is the exponent in the direct product testing theorem. So it should also be around doubly exponential. Okay, so now I will tell you some of the ideas to prove this theorem. But before that, let me introduce, so also the corollaries, we get some immediate corollaries to hardness of approximation. So if you assume the exponential time hypothesis, which says that deciding 3-SAT takes exponential time, you get that approximating 3-SAT with a factor that is better than randomly guessing actually would take time 2 to the n by polylog n. And similarly, you also get that assuming exponential time hypothesis, approximating a system of linear equations where every equation could even just depend on 3 variables with a factor that's better than, again, randomly guessing, should also take time 2 to the n by polylog n. Yeah. So now let me tell you something about our main result. And before that, let me introduce the protagonists of the talk, these objects called high-dimensional expanders. So let's recall what are expander graphs. These are very well-connected sparse graphs that have many of the nice connectivity properties that complete graphs possess. And high-dimensional expanders, for today's talk, we'll think of them as generalization of expander graphs, where additionally, every local neighborhood is also an expander. So for example, in this picture that I've drawn, if you looked at this induced subgraph, and you looked at one vertex, then all the vertices in its neighborhood also form a small expander graph. So in particular, this kind of means that these graphs have a lot of well-connected cliques. And today we'll think of these graphs as having theta of n edges and theta of n well-connected constant size cliques. So if you're familiar with HDX, I'm talking about the one skeleton of the simplicial complex of an HDX. But if you're not familiar, you can ignore that comment. So a priori, it's not even clear that these objects exist. But yeah, so these are the cliques. But remarkable work of Lubotsky, Samuels, Vishnay, followed by a lot of later nice works, showed that these objects exist. Okay, so let me talk about how we use HDXs in different ways, starting with gap amplification. So what we want to do is start with a 3-sat instance whose value is either 1 or not equal to 1. And finally reduce it to a 2CSP whose value is 1 or close to 0. And in the process, we only want to blow up the size by polylog n. So as a first step, we can already use Dinur's PCP to get to some value which is bounded away. So some value which is like 0.99 and incur a polylog and blow up. So what we'll be thinking about is this step of the reduction. So let's see what's the known technique for amplifying the value to 0. And let's start with this technique called parallel repetition. So suppose you're given a 2CSP on G, and it's promised to have value 0.99. One way to amplify the value to 0 would be to pick k random constraints. So suppose you had an assignment that has value 0.99. If you picked k random constraints and checked whether all the constraints are satisfied by that assignment, you would get that this holds only with probability 0.99 to the k. So this is the intuitive idea behind parallel repetition. But if you just did this, you would get a k-CSP, but we want to get a 2-CSP. So the idea is to create this larger graph, phi tensor k, whose vertices are k tuples of edges. So every vertex here consists of k edges. And you put in an edge between two vertices if they have some significant overlap. So here T1 and T2 intersect in square root, roughly square root k vertices. So now to create a constraint satisfaction problem, one natural thing that you can do is that firstly, you ask for an assignment where to T1, which is going to be a 2k tuple of values, which is supposed to be the corresponding assignment to the 2k vertices on the left, and similarly for T2. And to check a constraint, you will check whether all these 2k tuple of values firstly satisfy all the edges in T1, and similarly all the edges in T2. And additionally, the 2k tuple given to you here and here is consistent with these. So any questions about the definition?
So why is there a square root k? In the...
Oh, yeah, okay, that's a typo.
Okay.
Okay, so just as a example, suppose phi had a satisfying assignment F1 to Fn. Then it's easy to see that phi tensor k is going to have a satisfying assignment where to every vertex t, you just assign the 2k bits, which is f restricted to that set. But really, the interesting question is what happens in the reverse direction. Suppose phi tensor k has some high value via a set of local assignments to every set. Can we say that phi has high value? Now, this is non-trivial because these set of local functions may be actually restrictions of various assignments. And maybe they are cheating in the sense that they do not actually correspond to one single assignment.
The overlap is on edges or on vertices?
The overlap is on vertices, like around square root k.
Between these 2k and these 2k, there has to be an overlap.
Yeah. Yeah, so other questions about why this is non-trivial? Okay, so yeah.
A different question. Like, what do you mean by significant overlap? Like roughly how many?
Roughly, we'll think of it as like square root k for this talk.
Is there like a simple reason why it's square root, or is it just like what?
Yeah, maybe I'll flash the theorem. So actually, this is highly non-trivial, and Raz showed that, in fact, it is true that if phi tensor k has value around 0.99 to the square root k, then phi has value 0.99. I slightly modified Raz's theorem to make it relevant to the talk here.
Yeah, but just to be accurate, Raz showed it with k, not with square root.
Yeah, Raz showed it with
So-
k.
Right,
and
so
it
square
was-
k, it's easier to prove.
Yeah,
It's a weaker theorem, it's good enough for that.
yeah. Yeah, so Raz's theorem was actually more powerful than what's written here. And it wasn't like exactly this kind of amplification.
And then IKW showed something that's weaker, but later, and so,
Yeah,
I'm just kidding. But to answer your question, it's much more expanding when the overlap is smaller, right? So you can imagine it's easier to prove when there's less correlation between them.
yeah, so yeah, thanks, Arif. And yeah, when you have overlap, let's say I, you get like 0.99 to the I.
So this is unrelated. What is the easier proof of this? Can you sketch it? Or
Yeah, I will try to.
We'll get to that.
we'll get to it.
Yeah. Okay, so this is good, but basically this reduction has a size blow up of n to the k. So can we get some error decay by choosing only a small subset of the vertices of phi tensor k? So Goldreich and Safra, just trying to think what they would have thought, that this picture is getting pretty complicated. Can we simplify the question? So can we just think about some combinatorial question that does not involve CSPs, checking constraints, etc. And they considered the following question. So just we have just a simple encoding of f into k bit strings. And now let's consider the reverse question. If H is a set of strings that are locally consistent for many intersecting pairs, can we stitch them together into one global function? And formally, they defined this direct product code. So fix some set system S, let's say this, and the direct product encoding of F using S just writes down the restriction of F on all the sets in S. And the main question here is that suppose you have given an arbitrary set of strings that look locally consistent for most pairs TI-TJ. Does H have to be close to the direct product encoding of some function F? And again, more formally, you can consider the two-query test, which picks Ti and Tj in the set system with this intersection size and accepts if H of Ti and H of Tj are consistent on the intersection. And we want this test to be complete, that is a direct product encoding. Second. And this holds. But we also want it to be sound. I can in the sense that if H passes this test with probability epsilon, then we want it to be correlated to a direct product encoding of some function. That is, H of T should be equal to dp, direct product encoding of F, for many H's. And basically, the goal is to find a sparse set system S so that the direct product test is 0.01 sound on S. So let me tell you what was known about this test. So firstly, in 2005, Dinur showed that the constant-sized neighborhoods of an expander graph support a direct product test with soundness close to 1. Yeah, this is a modern interpretation.
It's not really what was shown there.
Yeah.
Yeah.
Like
It's more, you're right.
in your later work
Interpretation.
of Yotam.
Yeah.
Yeah. And by soundness close to 1, we mean that when the test passes with probability close to 1, you get correlation with some direct product function. And this was like one of the main ingredients in the gap amplification step. But shortly after, Bogdanov showed that this test is not sound, does not have soundness even half. So to find set systems that have soundness close to 1, Dinur and Goldenberg studied the complete set system, where you have all possible sets on the universe of size n, all possible constant size sets. And they showed that this has a soundness close to 0. And this implies the weaker form of the parallel repetition theorem that I had shown on the previous slide. So really, the question still remained whether we can get sparse set systems with soundness close to 0. And Dinur and Kaufman, motivated by finding other set systems, they looked at high-dimensional expanders and looked at the constant-sized cliques in a high-dimensional expander. And they showed that it has soundness close to, the direct product test has soundness close to 1. And they conjectured that there are high-dimensional expanders where the direct product test has soundness close to 0.
Yes, the point here is that the number of sets in the set system is O of n.
Yeah, so yeah, as I had said on the previous slide, the number of constant size cliques in a high-dimensional expander is like theta of n. So that's why these are sparse set systems. Yeah, so fix this set system, which is the constant size cliques in a high dimensional expander. In previous work, concurrently with Yotam, Dixteen, and Dinur, we showed that the direct product test on S is sound in the close to zero regime, if and only if G possesses a form of topological expansion called coboundary expansion. And interestingly, if you look at the negative direction, that is, if G is not a coboundary expander, the test is not sound. This is a generalization of Bogdanov's counterexample. And then the question was whether we can construct high dimensional expanders that are also coboundary expanders. And then in later work with Noam Lifshitz and also concurrently in works of Dixteen, Dinur, and Lubotsky, was shown that there are sparse high dimensional expanders.
So it says it's sound if it's not a coboundary expander?
Oh, it is sound only if,
I think it's a type.
It is a coboundary expander.
oh yeah, okay, sorry.
Otherwise,
Yeah, sorry. Yeah, so you need this additional coboundary expansion property, which is also sufficient. And together, and these were variants of the high dimensional expanders constructed by Chapman and Lubotsky last year. And together, these two results imply that there are sparse HDXs for which the direct product test on this set system is sound. So let's go back to our question of parallel repetition. Can we use the HDXs to somehow get a sparser graph over here? So there are a bunch of things you may try here. For example, you could take the universe as the set of all k, all edges, and then you could take k subsets of the edges, but only those which belong to the high dimensional expander, so on. But none of them seem to work here. And in fact, there's a barrier to doing this kind of generically. You need to somehow use more properties of G. So we said that why do this? Let's instead consider very specific 2 CSPs. And let's say your 2 CSP is on a high dimensional expander. So the constraints only are on the blue edges. Now, what you can do is construct another 2 CSP where every vertex is going to be one clique, and you have an edge between 2 cliques if they have an overlap in square root k vertices. And now again, you ask the assignment of every vertex to be a k tuple of values. And the constraints are just going to check whether all edges in T1 and T2 are satisfied. And also the assignment to T1 and T2 are consistent. And actually, it's not too hard to work this out, but this is very immediate that just using the direct product testing theorem as a black box, we can get that if phi has value at most 0.99, then this resulting CSP has value close to 0. But now the size blow up is the size blow up in the direct product encoding. So it's only going to be by a constant factor. Yeah. I guess to answer Young's question, this is how direct product and this de-randomized parallel repetition are related. So what we wanted to do was this, but what we ended up doing is just a reduction from 2 CSPs whose constraints are on a high dimensional expander to 2 CSPs whose value is close to 0. So the natural question is whether we can do this arrow of the reduction. And in fact, that is what we do. So we find first a reduction, which converts an arbitrary 2CSP to a 2CSP whose constraints are on the high dimensional expander. But in the process, it blows up the alphabet by a lot. But let's ignore that for a moment. Then we can use the direct product testing theorems to reduce the value to almost zero. And finally, we can use like by now standard query composition techniques from the work of Moshkowitz, Raz, and Dinur and Harsha to reduce this alphabet down to a constant. This again results in a blow up of polylog n, but we are anyway okay with losing polylog n factors.
And this preserves that the constraint graph is an HDX.
Yeah, so this does not preserve.
Okay.
This would be like, I don't know, have some kind of HDX property, but this.
Oh, sorry, yes, okay, I see.
Yeah. Yeah, so actually we only need that constraint graph is HDX to do this step. Okay, so that's the summary of the reduction. And now I'll tell you just some small things about the first step of the reduction. So we do this part using fault tolerant protocols on HDX.
So just the previous work, if you wanted the constraint graph to be an expander, let's say you just add some edges, right, to make it an expander.
Yeah, so
But here it's
Dinur's-
more.
yeah, so in the Dinur's reduction, to just get an expander, you can add a expander, and that would make the value, like you lose, if it was initial value was 1 minus epsilon, you'll get value 1 minus 2 epsilon.
The problem is you can just add,
Minus epsilon.
you can just add an HDX and make it an HDX. It's
Yeah,
it's
you
not
can do,
monotonic.
yeah. Yeah, so let me describe this part of the reduction now. Okay, so this is what we want to do, where we have an arbitrary constraint graph here. We want to convert it to a constraint graph, which is an HDX.
You just wanted to say to him, so that's fine, that's an interesting kind of drawback of HDX. It's very rigid. You can't like take another graph and just make it into an HDX.
Yeah,
It's very hard to move in this space.
yeah. Okay, so yeah, this is what, yeah, we can't do like simple kind of, yeah, tricks. So this is what we want to do. And really, when we looked at this problem, there was only kind of one technique known to convert an arbitrary graph into a graph, specific graph with some specific structure. And this was done in works of Polishuk, Spielman, and Dinur. And their main idea was to break the original graph into matchings. So the original graph is going to be some constant degree graph. So you break it into D matchings. And then to route each matching on G. So for their purpose, they wanted to embed an arbitrary graph into a De Bruijn graph. So let's look at what routing means. So what's a routing protocol? So consider a fixed graph G and an arbitrary permutation on the vertices of G. And in this problem, every vertex wants to send a message to its friend pi of u. But these orange edges may not be edges in G. So it cannot just send it across in one step. But the question is, can you send it across using paths that only use edges of G? So for example, you may want to first send one's message to 2, and then 2 sends it to something else, and then so on. And now all the blue edges are going to be edges in G. And in this particular way that I've drawn, in each step, every vertex sends one message to one of its neighbors. And then the way I've drawn it, like here you again have a permutation. Yeah, this is a permutation and so on. And then finally you get the permutation you want. So at the final step, pi of 1 receives the message that 1 sent to it. Okay, so they were able to show that actually if G has a routing protocol, then every 2 CSP phi can be reduced to a 2 CSP on G, such that if value of phi is 1, then value of the resulting CSP is 1. So even this part is not immediate. Like how would you use a routing protocol to get a CSP only on the edges? So let me just at a very high level describe how this is done. So let's look at a simple CSP, which is just a matching. So here you have the orange edges, and each edge here has a constraint. And let's say it's satisfiable via this assignment A. But now the constraints are on the orange edges, and we want them to be only on the edges of G. So Dinur and Mir, what they did is to consider the routing of this matching. So now you have only, in this picture, each blue edge is an edge in G. And now you ask the assignment of every vertex to be a long table, where at the first step, it's the assignment of the vertex on the left. In the second entry here, it is the value that vertex 1 received in the second time step, and so on. And now, as you can see, at the final time step, because you've done a routing protocol, 1 will receive the value that pi of 1 sent it. So instead of actually checking, to check this constraint on the left, you had to look at the values of 2 vertices. But in this picture, you can actually just check it using the assignment of just 1 vertex. So any questions about this?
Does this routing protocol depend on your instance? Like for every instance?
Exactly, yeah. So phi, it depends on phi, because this orange edges, there is a particular way to route them. So if you had different permutation here, you will get a different routing protocol.
You have like a bound on the, I don't know what to call it, but like depth or something of the routing protocol, just
Yeah.
how many steps you need.
Yeah, so that's a great question. So firstly, to check this constraint, we can only look at one assignment, the assignment of just vertex number 1, and check it. But let's add some few more constraints that are going to be satisfied by A, which is that on the edges of G, you can also check, for example, on this edge 1, 2, you can check whether at every time step that 1 sent a message to 2, 2 received the same message. So here you will check that A of 1 and A of 1 are equal, like this entry and this entry are equal, and so on. And this actually, if you do this carefully, you can show that if value of phi is 0.99, then value of this CSP that we just constructed is 1 minus 1 over the path length. And now, as you can see, we are only checking edges of G. But the downside is, of course, the alphabet is a lot larger. The alphabet of every vertex here is going to be 2 to the number of entries here. So it's going to be, the log of the alphabet is going to be the path length. But now we have a one reduction which reduces an arbitrary graph to a graph CSP on a particular graph we want. So now let's examine this. This is not so good for us because if you have a constant degree graph, you would expect paths to be of length log n. So this would give us a reduction where 0.99 soundness goes to 1 minus 1 over log n. And the machinery that we have from direct product testing would then lead to a huge size blow up if you just applied it. So we really want to preserve the soundness. Even when we embed, we change the constraint graph. So if you examine this reduction, you would see that actually the loss in the soundness is because this routing protocol is not robust. If you corrupt even one edge on the path of length log n, the whole path fails to transmit the message. So what if we considered more general protocols called fault-tolerant routing protocols? So we have the same setup where we have a graph G and we have some arbitrary permutation. And again, U wants to send a message to its friend pi of U. But now we do not, we want to relax this stringent guarantee that, you send only one message at every time step. So for example, you could do more complicated protocols. For example, one sends a message to 3 vertices, and at the second time step, all these 3 vertices send a message to another 3 vertices. Then every vertex in this layer takes a majority of the messages it receives and then passes it on forward, and so on. So basically, you can do any protocol as long as it has 2 properties. So firstly, it should have fault tolerance, which means that if at most 0.01 fraction of edges of G are bad, like they behave maliciously, then at most 0.01 fraction of these message transmissions fail. And the second thing we want is efficiency. So we want every vertex in the protocol to perform around polylog n computation throughout the protocol. So recall that if you just did paths where every vertex is sending one message, this would be like log n, but now we are additionally allowing you extra computation, which is polylog.
Sorry, computation here just means like number of things sent and received, or I mean, you.
Yeah, so it encapsulates the number of messages sent and received, but you do not allow vertices to perform exponential time computations on the messages received. You can perform you can perform any computation as long as it's like a small circuit on the messages received. So any more questions about this model? Okay, so yeah, hopefully the model is clear. Okay, so basically you can use the same idea in the Dinur to actually get this general connection. So if G has edge-tolerant routing protocols, then every CSP can be reduced to a CSP on G, but now while maintaining the soundness. And now the alphabet blow up is going to be 2 to the polylog n rather than just 2 to the log n.
Sorry, is G a specific graph? It's not a graph.
So this connection just says that as long as G, which is a specific, which could be the graph of your choice, as long as it has these fault-tolerant routing protocols, then you can reduce arbitrary CSPs to CSPs on G.
So maybe later it will be more.
Okay, so Okay, so this edge, okay, I didn't realize it's a property of the graph itself, like.
Yeah, let me just say that more clearly. So you consider a fixed graph G, and G has like these fault tolerant routing protocols. If for every permutation, you can build a protocol which has fault tolerance.
So it's like you have G, you get to choose it. It's like a beautiful graph, whatever you want. And then someone brings you some CSP instance, which is arbitrary, and it's not beautiful. And you try, and you think of that instance as a bunch of permutations. And then you try to map these permutations into your one fixed G. Right?
Yes, yeah. So this is whether G supports fault tolerant protocols or not. It's just a property of G. And what we are saying here is that as long as G supports these fault tolerant protocols, you can reduce arbitrary 2CSPs to 2CSPs on G.
You need that like this routing protocol is computable like, efficiently. And it's like
Yeah.
built into the assumption.
Yeah, we also need because we want a polynomial time reduction, we also need a way to find such a protocol efficiently. But usually that turns out to be easy to do. Okay, so recall that we wanted to reduce two constraint satisfaction problems on HDX. So what this connection tells you is that all you need to do is to build fault tolerant protocols on HDX.
Mitali, like in this fault tolerant definition, are there like natural or like well-known graphs that have this?
Yeah, so I'll get to that now. Yeah, so our question was where do we even start to build such fault tolerant protocols? But fortunately, this question had been considered long back in the literature in a work of Dinur et al. And their main motivation actually came from distributed computing. They wanted to find sparse graphs that support distributed computing in the presence of malicious parties. And prior to this, like distributed computing protocols or multi-party computation had only been considered in the setting where you have a complete network between all the machines. And their main open question was the same thing that we are kind of asking. Are there sparse graphs with fault-tolerant protocols, but actually handling, constant fraction of vertex corruptions? So, in fact, in literature, lot of works tried to, improve whatever Dinur et al. Did. And actually, let me mention that the first network that they gave was a butterfly network. It's very similar to the De Bruijn graphs. But that routing protocol is actually, again, using just edges, like sending along log n length paths. So again, it's not tolerant to constant fraction of corruptions.
Just from my understanding, would like a random graph be, like a random 100 regular graph be fault tolerant?
No, I don't think so, at least. So a random graph would be an expander, and actually like these kind of protocols that I just showed where you just send along paths of length log n, these are true for expanders too. Like you can find such protocols for expander graphs. This was shown in works of Alone et al.
Sure.
But again, they are not fault tolerant.
Why?
So you're sending one message only along one path. So again, if you corrupt one edge, you corrupt the whole path. So it leads to a fault tolerance only up to 1 by log n fraction of corruptions.
But
If you think how many edges need to be corrupted so that constant fraction of the paths got corrupted. So the paths have length log n. So if you corrupt 1 by log n fraction, you've hit a constant fraction of the paths.
Yeah.
So you moved from corruption of 1 over log n to corruption of a constant fraction. That's not what we're doing. What she's doing is moving from a constant to a constant. You can tolerate it.
So in these graphs, a lot of paths will be short, like super short. I mean, that's not possible, right?
Yeah, so I'll get to that.
No, wait, I don't understand that comment, because that's only one protocol, right? A protocol where I send like one path to one message. Couldn't it be that expander graphs have a more sophisticated protocol?
Yeah, so what these works did was to try to improve what Dwork et al. Did. So actually what they did, kind of the networks in these graphs are taking an expander graphs and adding cliques to them so that you can perform error correction. So you do not send one message along one path, but you send it to a clique, the clique performs some majority vote, you send it to another clique and so on. So one thing is that actually these protocols do not tolerate edge corruptions. They are only resilient to vertex corruptions. And one thing is we also can't use these directly because we need to show that specific graphs, which are these HDXs, have these edge tolerant protocols. But this is nice because when we saw these results, they actually plant cliques in the graph, whereas HDXs already have so many cliques. So they are built to have these protocols. So in fact, if you take an HDX, which is a sufficiently good high-dimensional expander, it has degree polylog n, and actually the smallest eigenvalue, like the local spectral expansion is around 1 by polylog n. Then you can get edge-tolerant protocols, and every vertex performs around polylog n computation throughout all the protocols. So these are inspired by these error correction ideas. And actually it improves on the prior work because the prior work could not construct protocols that can tolerate edge corruptions. So in the vertex corruption model, it can be thought of as you corrupt edges that only occur on a constant fraction of vertices. Whereas in the edge corruption, you can corrupt an arbitrary constant fraction of edges. So one protocol that we can do on an HDX would be to, one vertex here sends its message to everything in the clique T1. And then the clique T1 passes the whole message to a clique T2 that has some good overlap with it. And you keep passing the message only along cliques, but not along a single path until it reaches the final destination. So in fact, basically we did start out with this clique-to-clique protocol, but it doesn't give the parameters needed. So we moved to other well-connected dense subgraphs in an HDX called links. And the analysis of these protocols uses a lot of nice concentration bounds that are known for HDX. So the clique-to-clique protocol can be analyzed using Chernoff bounds that were proved by Dickstein and Hopkins. And like the other more complicated protocols you have use only spectral expansion properties. Okay, so actually, even though the previous Dwork et al. Only cared about vertex corruptions, turns out that to construct constant degree graphs with these fault-tolerant protocols, we can perform some nice graph product style composition, similar to the composition in expander graphs to get.
Sorry. So does this work simply because the diameter is small, or actually it works because of more complicated reasons?
So one thing is that you always need the diameter to be small, otherwise your vertices may not be reachable. But additionally, it also works because you have this very nice structure of having many, many cliques.
By small, I mean like a constant or, okay, no.
Oh, it's not, no. So since the degree is like polylog n, you can only hope for diameter, which is like log n by log n, something like that.
Okay.
So you do still need to go a long way before reaching your destination, but you do, every step actually does error correction on the previous message.
Is it really important if the local things you're routing on have constant diameter?
Yeah, so for example, if you routed on cliques, yeah, the local things you're routing on have constant diameter. So one vertex sends its message to a clique that has a constant diameter, so it can quickly error correct what the original message was, and then send it to another clique, which again performs some error correction and sends it forward.
So it's a link, it's not, no, it's a link of size polylog.
Yeah.
The diameter is like log of length.
Aren't the
The
buildings
links
constant diameter?
Yeah, the links are like spherical buildings, so we just use they have constant diameter.
Okay, I mean.
You just like use one neighborhood, so it has a constant diameter. Because the degree is also
The
polylog.
degree is polylog and the dimension is polylog.
Yeah. Yeah, but the link itself is constant diameter.
Okay.
Yeah. Yeah, actually, in tomorrow's talk, I will explain more about this routing protocol. So at a very high level, why it works is because when you just send one message, that message fails only with probability 1/log n. Whereas if you send it on a path, each edge fails with probability constant. So now you have paths of length log n, but each edge in the path fails with probability like 1/log square n. So your message reaches with probability like 1 - 1.
How is this graph you're talking about constructed out of the simplicial complex?
Yeah, so I actually was going to mention that. So you can use this HDX with routing protocols along with this general connection to get an embedding onto HDXs. So this is just a summary of the previous thing I talked about. And actually, Yoon showed that you can take G to be the HDX that we want in the direct product testing result. And it satisfies additionally these properties that it has degree polylog n and spectral like lambda 2 very close to also 1 by polylog n. So basically you can take G to be the same graph that has both the nice properties. Sorry, what was your question?
Sorry, I'm asking about something simple I don't understand. What I know, is the definition of an HDX. It's some set system. I'm just asking, how are you thinking of it as a graph? That's all.
Oh, yeah, okay. So I'm just thinking of as a graph as the vertices and the edges in that in the simplicial complex.
So if you look at a set system, for every set in your set system, you put a click on all those vertices, and you have a graph.
Okay.
And then just think of the graph.
Okay.
Yeah. Yeah, so any more questions about this?
So this work of Yoon, what they actually do is like construct like these HDXs or like the dimension and the degree scale. Like, is that what?
No, yeah,
is
it's
right?
so it's just maybe even simpler. So like if you know the field size is Q,
Yeah.
we want the field size to be like polylog n. In usual HDX constructions, like even in yours and stuff, we don't know like the parameters are such that you choose Q and then n can be very large, and you don't have a bound on how large n would be. But here we want Q to be polylog n and then the number of vertices to be n. So that's what he's able to do.
And dimension like log n, right?
No, so the dimension in the final HDX that we want is still
That's
constant.
fine.
The distributed stuff, does it have applications, I mean, on its own? I mean, it seems like a new way to do this kind of routing. I mean, using HDXs.
Oh yeah, the application I mentioned was here, like we could solve this Dwork et al. problems.
I know, but does that have applications in practice or in anything else?
So they were motivated by doing like MPC on sparse graphs. So that would be, so there were works that showed that once you get a sparse network which has fault tolerant protocols, that sparse network supports any distributed computing protocols known for complete graphs or any secure multi-party computation protocols. So you can now do all the protocols you have on the complete graph, but on a sparse graph.
I mean, it might have future applications that are more complex.
Yeah. Yeah, and also there might be applications that I am unaware of. Like I'm very, and I've just looked at this literature. Yeah, so this is a summary of the reduction. And one like nice thing I wanted to mention was actually we can actually get amplification also using this fault tolerance. So it's an alternative technique in. So what we can do is actually amplify 2 CSP with soundness 1 - 1 by polylog n to 2 CSP with value 0.99 using this fault tolerance routing protocols. So it's an alternative to Dinur's amplification only in this regime. I mean, so Dinur's amplification works across the whole regime, but yeah. Yeah, finally, I'll just mention few open questions. So one thing is, could you improve the size efficiency, to get the constant in the polylog to not be dependent? So this might look like, I don't know, not so interesting, but I will mention some nice, it actually, one way to do it would be to just get routing protocols on constant degree high dimensional expanders. So that, yeah, that's very interesting question, combinatorial question. And then, size efficient PCPs in the low soundness regime and other applications of fault tolerant protocols. Thanks.
So any more questions?
So actually, maybe one question about the last question. Is it
Last slide.
the last open question?
Oh.
Yeah. Do you think that like these fault tolerant protocols can actually be used like in an algorithmic way, maybe to solve CSPs or something?
Oh yeah, that would be very interesting. Yeah, currently I know only of simulation results, like you could use it to simulate protocols on complete networks.
For example, you mean you would map your CSP to an HDX one?
Yeah, then I would actually try to
beat the exponential time hypothesis and HDX.
Yeah, okay.
Maybe not a general CSP, but like it seems as though you're mapping some CSP to some CSP that maybe has nice structure, right? So
Yeah.
Yeah.
Was a paper about approximating CSPs on HDXs.
Yeah, so I think their alphabet, yeah, so their alphabet, our alphabet is really large.
Yeah, compared to Applied doesn't
Yeah.
give you anything, but like just to kind of answer your team's question, there might be something you can't do.
Yeah, so there was a paper on actually solving two CSPs on HDX. Or K CSPs on like where the constraints are the K sets of the HDX.
Yeah, in both ways, right? Some papers
Yes.
are on hardness and some are on
Yeah. Yeah, so this falls into proving hardness. But I think the setting in this paper of Tulsiani et al. Is also the same thing. You have a 2 CSP on the edges of the HDX, but there the alphabet is small. Here we have NP hardness when the alphabet is large.
Oh, I see. So you mean it's the same setting where they solve it?
Yeah.
But just because the alphabet is large, then their algorithms
Yeah, actually, you could also do like algorithms on expanders for two CSPs. Like there's these algorithms of Barak rather than that stuff.
No, but those really depend on the alpha size.
Yeah.
So it's similar.
Yeah,
It's the same algorithm.
Yeah,
They use
yeah, so-
VRS, except they split the K set in half instead of splitting it in half, it's supposed to be like it's.
yeah.
Okay, so thank you so much for a very interesting talk.